You want to use pretty much everything you've learned up to this point to graph these functions. You want to find your maximums and minimums. That would occur when your first derivative is 0 or undefined. You want to look for the intervals where your function is increasing or decreasing. It's increasing when your first derivative is positive. It's decreasing when your first derivative is negative. You want to find your inflection points, and they'll occur when your second derivative is 0 or undefined. You want to go ahead and find the intervals in which it's concave up or concave down. That would be when your second derivative is positive for concave up or second derivative is negative for concave down. Find your x-intercepts and y-intercepts. Look for your discontinuities. If you have vertical asymptotes, you want to say, okay, what's happening on each side of my vertical asymptote? Just to the right of my vertical asymptote, is it diverging towards positive infinity, meaning going up forever? Or is it diverging towards negative infinity, meaning going down forever? And then you want to do the same thing just to the left of that vertical asymptote. You then want to look at your end behavior. That's your limit as x approaches infinity or negative infinity. Is it leveling out at a particular height, a particular number? If so, then it has a horizontal asymptote. Is it leveling out as you approach a diagonal line? Then it's a slant asymptote. Or is it approaching a curve as you go far off to the right and to the left? Then it's an oblique asymptote. You want to use all that information then to be able to go ahead and sketch your curve. Now, if we do all that for this particular problem right here, we would get the graph up here. We have our x-intercept, x-intercept. Our y-intercept. We'd have a horizontal asymptote right here. We'd also have a vertical asymptote, and that's what causes the bottom to be 0. We also have little pluses here. Wherever you see the pluses, that means your function is going up, increasing as you go to the right. Wherever you see the negatives, that means it's going down as you go to the right. And then here, you're increasing again. The little horseshoes here are for your concavity. Here, you know it's concave up. Here, it's still concave up until you get to here, and then you're concave down. So we want to find all that information for this problem here. I'm going to just go ahead and rewrite this. I'm going to do the synthetic division. Take the opposite of what's down here in your half box. Put the numbers afterwards, the 1, the negative 1 here, and it gives us this. So we could rewrite it as an x plus 2 plus a 1 over our divisor. This form here will help us with a couple of things for this particular problem. Now, to find your y-intercept is when your x-coordinate is 0. So you plug in 0 into your original function and you get 1. To find your zeros, which is your x-intercepts, you set your function equal to 0. Well, your function's equal to 0 only when the top is equal to 0. Then you can use your quadratic formula. You get these for your zeros, but for the sake of graphing, you probably want the decimal approximations. To be able to figure out maximums and minimums in increasing and decreasing, we need to look at our first derivative. So we'll take our first derivative, and in this case, I just did the derivative of what I was looking at right here. Derivative of your x is 1, the derivative of your 2 is drops out, and then this here works down to be this. Then we can simplify this because we need to go ahead and set it equal to 0 to solve it. And when is it equal to 0? Well, a fraction's equal to 0 when the top is 0, so you're going to have critical points of 0 and of 2. But you're also going to have a critical point at 1 because that's where your first derivative is undefined. Because remember, your critical points are where your derivative is undefined or 0. You then want to go ahead, put them on a number line. Here's your points on a number line. Notice it's labeled as your first derivative. Then you want to take a number in each region here, plugging it into your first derivative. So we could try negative 1 over here, plugging it in, and we end up getting a positive, which means your first derivative or your function is increasing, so I'm drawing an arrow or a line going up. Try a number in between into your first derivative, ends up being negative, which means it's decreasing, so I'm going to draw a line going down. In between the next two, I'm going to try 1.5 into your derivative, and I get positive, or another negative, so I know it's decreasing. So I'll draw another line going down. A number to the right of 2, I'll plug in here. It's positive, so I know it's going up. So when I have a mountain, that means that's a maximum. When I have a valley, bottom of a valley is a minimum. So I do have a local maximum. How do I figure out the y-coordinate? I actually have to plug 0 into my original function. And I get 1. I have a local minimum at 2. So how do I figure out the y-coordinate? Plug that into my original function. Plugging it into my original function, I get 5. Now we need to pretty much go ahead and take a look at our second derivative. Do your second derivative of this. Notice the derivative 1 drops out, so I'll just take the derivative of this. I get 2 over the bottom cubed. Your critical points occur at whatever causes this bottom to be 0, because you can never divide by 0, meaning that's when your derivative is undefined, or at what causes the top to be 0, because that's when it would be equal to 0. The top's never 0, so we don't get any critical points from that. So now we want to do a number line again so we can check our concavity. This is for our second derivative, so I'm going to check numbers on each side of 1 into my second derivative. Take a number to the left of 1 and plug it in here and see what I get. And when I do that, I end up getting a negative, which means it's concave down. Try a number to the right of 1, plugging it in. It ends up being positive, so then I know it's concave up. So I can write my concavity. I know I'm concave down when I'm from negative infinity to 1. And I know I'm concave up then from 1 all the way to positive infinity. We also need to go ahead and find your vertical asymptotes. Vertical asymptotes are what causes the original problem to have a 0 in the denominator. What causes this to be 0? That would be x being 1. So we have vertical asymptotes at x being 1. Whether you want to look at it here or again have it listed down here doesn't make a difference. Your slant asymptote, we need to look at our limit as x approaches infinity. It's easiest to take your limit, not of this one here, but of the simplified one here. As x approaches infinity here, this approaches 0. So you're left with just your x plus 2. Another way to look at it, when you're looking at a slant asymptote, you do your division, and you're only looking at your quotient. And it's going to be y equals whatever your quotient is. So we get a slant asymptote of x plus 2. Now going ahead and graphing all this, on your graph you want to plot your slant asymptote as a dashed line, do your vertical asymptote, plot your x-intercepts, your y-intercepts, plot your maximums and your minimums. When you've done all that, you get this graph here.